Hello, everybody. Welcome to another edition of Quinn's Weird Chemistry Lectures via YouTube. So today this is the end of the unit, right? It's the last lesson. And it's a pretty short one. So it's a nice way to kind of wrap it up. Not too much math, very little math. So this video should be short and sweet, I'm hoping. So let's get right in. So the intention is to describe, so we've been talking about solutions, right? So today we're going to describe how the addition of a solute, which is a fancy way of saying adding something that, maybe that could be pouring salt into water, right? Pouring sugar in water. So adding that dissolved substance into this solvent, how does it affect the freezing and boiling points? I'm going to mention a couple other properties, right? You'll notice the title of this lesson is like, how do I say that? It's colligative properties. All right, and we'll break that word down in a second here. But really, we're going to focus just on, very simply, when I add solute to a solution, so if I add more sugar to water, how does that affect the freezing and boiling point of the solvent or of the solution? Okay, so let's jump right in. So something to think about, and I'm going to ask you this again at the end of the lesson, so I'm not going to answer it right here. So take a moment, pause, and think, why do we salt the icy roads in the winter to make them safe? Why do we throw salt everywhere? Right? On the sidewalk, on our front porches, right? What is that doing? And why don't we use something like sugar? Why do we use salt? Okay? Think about that, pause, maybe ask a parent or something, see if they can figure it out. But keep that in mind when I go through this lesson. Okay? Maybe it'll dawn on you in the middle of this. Okay? So, before we get into colligative properties, let's just talk about physical properties of matter real quick. And most of this stuff you don't absolutely need to know, but it's good context. So we can divide all physical properties into two categories. Extensive properties, right? So this is mass, volume. These are things that depend on the size of the sample, right? If I have, 1 gram of sugar and I add a bunch of more sugar, now I have like 10 grams, okay? Mass has changed. That's an extensive property. The volume has also changed, right? Now it's a bigger pile of sugar. It's taking up more space. So extensive properties depend on the size of your sample. Intensive properties, this is like density and concentration. These are characteristic properties of the substance, and they don't really depend on the size of the sample that are being studied, right? If I have 1 drop of water, the density is 1 gram per milliliter. If I have an ocean of water, not salt water, but let's say a lake then, a lake of water, the density of water is still 1. It doesn't change depending on the size. Remember yesterday, the lemonade example. The whole pitcher of lemonade has the same concentration as a single glass. It doesn't matter the size, it's just about, so the size of the sample doesn't affect the intensive property, like density or concentration. Okay? So extensive properties, size matters, the size of the sample matters. Intensive, the size doesn't matter because the property is always the same. There's a third category, sort of. It's actually part of the intensive properties. So this is something that doesn't change depending on the size of the sample being studied, and that would be colligative properties. Okay, now colligative means depending on the collection. Okay, so colligative properties depend on the collective effect of the number of solute particles. So this only applies to solutions, right? You wouldn't talk about the colligative properties of water. That's not a solution. It's just that's a pure substance, right? That's a compound. So this only applies to solutions, right? Which is what we've been talking about the past few days anyway. So this is important here. Why is in bold, underlined, right? Colligative properties only depends on the ratio of solute particles to solvent particles. So it only matters how many solute particles you have. It does not matter what the solute particle is. It doesn't matter if it's salt or sugar or anything. It just matters the number of things, the number of solute particles. Doesn't matter what the solute particle is, just the number of solute particles. Okay? So here are the effects that adding more solute particles, again, doesn't matter what they are, could be NaCl, CaCl2, sugar, right? Doesn't matter what it is. If you add more particles to solution, So if I put more salt in my water, I put more sugar in my water, it lowers the vapor pressure. Okay, and then that one, uh, we're not going to focus on that one too much. The next two we are. It also raises the boiling point. Okay, so for example, people when they're making pasta might put some salt in the water, and you might think that's just for taste, but it also does another thing. By putting salt in the water, it raises the boiling point. So now, when the water's boiling, it's actually over 100 degrees Celsius. Maybe it'll be like 103, 104. What does that do? Well, it's going to cook your pasta faster. It actually reduces the amount of time you need to cook it because it's now cooking at a higher temperature. All right, so putting salt in your pasta water actually cooks it faster because the boiling point has been raised because you added salt to your solution, your saltwater solution. So adding solute particles raises the boiling point, but it lowers the freezing point. Okay, so it makes it, you need a lower temperature to freeze that substance. Think back to the do now. I'm not going to give the answer away yet, but think about the do now question. Um, so yeah, the ones we're going to focus on are the boiling point and freezing point. Okay, so adding solute particles raises the boiling point and lowers the freezing point. It also affects osmotic pressure, which don't be too concerned about this. I don't know if you talked about osmotic pressure in living environment or biology, but that's basically, if you remember osmosis, right? That's the transfer of water through a membrane. Um, and if you remember, right, if you have really like a cell with maybe like lots of salt in it or something, water's going to rush in to dilute the salt, right? There's a pressure associated with that, right? That push of the water pushing on the membrane, that's osmotic pressure. So solute particles, that's another colligative property that depends only on the number of particles. Um, we're not going to focus on vapor pressure or osmotic pressure. We're just going to focus on the freezing and boiling points. So the two bolded ones there, right? These are the ones that you got to know. This is a little bit extra. I just like to include that because it really kind of fills it out. It shows you that there's more colligative properties than the ones we're going to focus on. But you take one thing away from this slide, or two things, okay? Uh, Colligative properties only depends on the numbers of particles that are dissolved, not what they are. Doesn't matter what they are. And when you have more dissolved particles, it raises the boiling point and lowers the freezing point. Okay? So we have to know there's something a little different here, though. How many solute particles are in the solution, right? We have to know. If I'm looking at two solutions and I'm like, all right, which one's going to have a higher boiling point? I have to know which one has more particles dissolved. Now, for ionic compounds, it gets a little tricky. Okay, I'm going to do a few different examples here, but they're pretty quick. Because ionic compounds dissociate in water, right? If we look here, CaCl2, that looks like, you can consider that one particle. But when you put it in water, all the ions break apart and you actually get one calcium and two chlorines separated. So this actually becomes three different particles, right? One calcium, two chlorines. Okay? So if I have 2 moles of calcium chloride in water, I actually have 3 times as many particles. So it's 3 times 2. This is 6 moles of particles because, right, each one of these is going to break up into 3 pieces. So easiest way to do this is you multiply the number of moles by the number of ions in the formula, which is really going to be, in this case, it's the number of atoms. It's not always that simple. So this breaks up into 3 ions, 1 calcium, 2 chlorines. So I multiply 3 times 2. There are 6 moles of particles. All right, I'm going to do a bunch more examples. 2 moles of sodium chloride. Now, sodium chloride will break up into 1 sodium and 1 chlorine. So it's really 2 particles, right? There are 2 particles per formula unit. So 2 times 2 is 4. There are 4 moles of particles here. So this solution, 2 moles of CaCl2, has 6 moles of particles, right? And 2 moles of this only has 4, so the boiling point of this will be higher because it has more dissolved particles. Okay, a few more practice questions. 2 moles of NaOH in water. Now careful here. you might think, oh, one, two, there's three different particles that it's going to break into. No, because this is a polyatomic ion and this will not break apart. So you're going to get, when this dissolves, you're going to get one Na and one OH. This is hydroxide. This is a polyatomic ion. So you get two particles. 2 times the 2 moles is 4. So you have 4 moles of particles here. Okay? Another example like that. If I have 1 mole of NH4Cl, hopefully you recognize NH4, that's ammonium. That's a polyatomic. So this is going to break apart into NH4 and Cl, which is 2 parts. So 2 times 1, 2 moles of particles. Okay? Last example, 0.5 moles of KCl in water. KCl, this one's pretty simple. It's going to break up into K, potassium, and Cl, chlorine. So that's going to give me 2 particles when it dissociates in water or dissolves in water. Right? And there's 0.5 moles, so 0.5 times 2 is 1. This will create 1 mole of particles. Okay? I went through that fast. However, this is a video, so please rewind and make sure you understand this concept, right? So this is different than something like sugar, which is a covalent compound. That won't break apart. But if it's an ionic compound, all these examples are ionic compounds, right? You have to think about, okay, I have 2 moles, but that's going to break up into 3 particles each, so it's really 3 times 2, a total of 6 moles of particles, okay? So go ahead and rewind if you need to, or not. Just keep listening. We're moving on. All right. So let's do some example problems you might see. So number 1, compared to a 2 molar aqueous solution of sodium chloride at 1 atmosphere. Okay, 1 atmosphere or whatever. They're both at 1 atmosphere. We can ignore that. So 2 molar NaCl. Okay. A 3 molar NaCl. So same thing at 1 atmosphere. So right here we're looking at 2 different solutions. We have a 2 molar solution and a 3 molar solution of the exact same thing. They're both of sodium chloride, which is salt water. So the 3 molar solution is going to have more particles, right? This means 3 moles per liter. This is only 2 moles per liter. So because the 3 molar solution has more particles, it's going to have a higher boiling point and a lower freezing point. So, but the question's asking about the first one. So it says compared, well, let's see, hold on. Compared to a 2 molar solution, a 3 molar solution has a higher boiling point. Oh, so it's going to be D. Higher boiling point and lower freezing point. All right. If you have more dissolved particles, you have a higher boiling point and a lower freezing point. Okay. Number 2, compared to pure water, okay, so nothing dissolved, an aqueous solution of calcium chloride has, well, if it has more, right, this solution has more dissolved particles because this one has none. So an aqueous solution of calcium chloride has a higher boiling point and lower freezing point, B. Okay, so the answer is actually the same, right? This one's D, this one's B, but they're the same wording. Higher boiling point, lower freezing point. Okay? And this last one here, make your own ice cream, right? You can actually use this to your advantage. It's too bad we didn't get to do this, but if you have, this works best with coffee creamers, like the little individually packaged ones, because they're already in a little container. But essentially what you can do is you put ice in a bag, and you put the creamer in the bag. Now, that ice is not cold enough to melt it, or sorry, to freeze the creamer. But if you put salt in the bag too, what you're going to do is you're going to lower the freezing point, making it's going to turn into, as the water melts, it's going to dissolve the salt, and the liquid water is going to get so cold, it's actually going to be below 0. Liquid water that's below 0 because you lowered the freezing point. And so now you're going to have those little creamers sitting in the super cold water, and that water will be cold enough to actually freeze the creamer, and then you can open it up. It should be solid. You can eat it. Actually, make sure you get a flavored creamer, though, because the regular creamers that have no sugar taste pretty terrible. Or they're not terrible. It's just weird, right? It's like frozen milk instead of frozen ice cream, right? We can talk about that in the meeting if you guys want to really go over how to make your own ice cream. But for now, right, we want to make sure we understand a few things. So take a minute, pause, answer these few questions here, unpause the video, and I'll go over them. Okay, hopefully you paused. So why do we salt icy roads to make them safe in the winter? Well, because when we salt the roads, right, it lowers the freezing point of water so it doesn't freeze. Because we throw so much salt down, and it only depends on how much stuff is dissolved, right? So by salting the roads, we lower the freezing point of water, so now the roads don't freeze. The freezing point becomes so low that the outside temperature isn't cold enough to freeze the water, so we don't get icy roads. Now, why don't we use sugar? Well, actually, you could use sugar if you wanted to, right? Sugar would dissolve in water and lower the freezing point. However, we don't use sugar, well, probably because it's more expensive too, but salt, remember, ionic compounds, they break apart into ions and actually make more particles. So real quick, remember when we did all these examples here, we noticed, right, we don't just have 2 moles, we have 2 times 3, which is 6 moles. And here we have 2 times 2, which is 4 moles. So ionic compounds, you actually need less of it because it breaks up into more particles, and all we care about are the number of particles, right? Colligative properties. It only matters on the collection of particles, not on what the particle is. So sugar, C6H, well, sugar would be what? C12H22O11. That doesn't break apart because it's a covalent compound. So for each molecule of sugar, you only get 1 particle, right? Whereas an ionic compound breaks up into multiple pieces and you get more particles. So salt is just more efficient, but you could throw sugar down on your steps to prevent it from freezing. It wouldn't be as efficient, and I think it would probably be more expensive, I'm assuming. I'm not really sure the price on sugar versus salt. Okay, number 2. Which sample, when dissolved in 1 liter of water, produces a solution with the highest boiling point? Okay, so if we're looking for highest boiling point, we're looking for most particles, right? The more particles, the higher the boiling point, and the lower the freezing point. So which one of these has the most particles? So right away, I can get rid of the 1 moles, right? A and C go away immediately because 0.2 moles is more than 0.1 moles. So it's either B or D. Now, they both say 0.2, but potassium iodide breaks up into 2 particles, right? Potassium and iodine. So you get 2 times 0.2, which is just 0.4 moles of particles. Whereas D, magnesium chloride, breaks up into 3 pieces, 1 magnesium and 2 chlorines. So this is 3 times 0.2, which is 0.6 moles. So the answer is D. Okay? Right, we're looking for the greatest number of particles, which would be D, because it's 0.2 moles, so it's already more than C. But the ionic compound breaks up into more pieces, right? 0.2 moles of potassium iodide has less particles than 0.2 moles of magnesium chloride because magnesium chloride breaks up into 3 pieces, whereas potassium iodide only breaks up into 2 pieces. Okay? So not a lot of math in this, but it can be a little confusing with all these different formulas and moles and whatnot. So this is a short lesson, so go ahead, rewatch certain parts, especially this part, right? This part can be a little confusing. But yeah, that's pretty much it. As long as you remember that if you increase the number of dissolved particles, you're going to increase the boiling point and lower the freezing point. Okay. All right. That's it for the end of this unit. Right. That's going to finish us off here. So on Monday, I'm going to have extended office hours from 11 to noon, and we will be able to review the material, and I will send out the assessment at noon on Monday. All right, so finish this today. The weekend is yours for chemistry anyway, and on Monday we'll pick it back up, and I'll assign the assessment at noon on Monday, which won't be due until Sunday the following week, so you'll have plenty of time to get it done. Okay, awesome. I will see you guys on Monday.